the spokesperson of the LZ experiment. He'll be telling us about that and Lux, I'm sure, and among other things. So take it away.
Okay, well, thank you for the invitation to be here. To be honest, the talk I have prepared here is the colloquium that I gave at Rutgers and Stony Brook last week. So this is the updated talk I have. So this is kind of an expert audience, so I'll try to speak about it at a higher level. But first, of course, I want to acknowledge the role that Texas A&M has played in these results that I have to show to you. Of course, this is the home of the Lux TPC. That's what the Lux TPC looked like when it was being assembled. Of course, this was designed and built by James White. And this is James, I think this is a picture taken here in his lab here at Texas A&M with the Lux TPC. I think maybe this is in the machine shop perhaps, or maybe it's in James's lab.
Shop tech.
This picture is James and his student Ty, who's now a postdoc. This is on site in South Dakota, I believe. I think this was a test assembly of the TPC because it's not in the clean room.
Yeah, that's in the surface lab.
At the surface lab where
outside the clean room.
Yeah. Right now, that very space is now this low radon clean room that's been installed for the LZ assembly. Here, James is dunking one of the plastic panels in liquid nitrogen. He did these extensive tests to understand how the plastic panels might warp or bend when the detector cooled down. And I think this is out on the loading dock here.
Yeah.
In the physics department.
You notice he has on all of his PPEs, right?
Does he?
Face shield on, gloves.
Yeah, of course he's exactly.
We don't need no stinking face shield.
It's Texas, right? This is the land of freedom, right? Regulations. So why are we looking for dark matter? So this is the explanation I give in my colloquium talks. Of course, there's many reasons. This is the one that I think is kind of simplest and very compelling. Of course, we know that the cosmic microwave background is an incredibly uniform radiation field, and that reflects the fact that the universe as a whole at that age of 400,000 years was incredibly uniform. This green oval, it looks like I just made a PowerPoint green oval, but in fact that's data. That's WMAP data, and that's what the cosmic microwave background looks like when you don't do contrast enhancement to see the anisotropies, right? So this green oval is representing the fact that the fluctuations are only 1 part in 10 to the 5, right? And your eye obviously can't see it, and the projector can't project it, can't give that kind of distinction anyway. So the universe was incredibly uniform at that age. Today, the universe has these vast overabundances of where galaxies are, and then vast voids in between where the galaxies are. So we have galaxy clusters, voids, all this incredible structure. So every dot in this plot is one galaxy. This is the slow digital sky survey. So we have, the universe has gotten from this state to this state in 14 billion years. And so how do you get from a uniform state to a clustered state? Obviously, gravity is what does that. And there's simulations that kind of show how that might work. The video to run. So first you run gravity forward, and it causes overdensities to collapse, and structure can form. So you can get from here to here in 14 billion years, but the problem is that you can't get from here to here if the only sources of gravitational potential wells in this initial state at this age were due to baryons. So because this is so uniform, there is 1 part in 10 to 5. If that was the only seeds for the gravitational potential wells at that time, you simply can't get to this state. We don't know how you get to this state in 14 billion years. So this is kind of too uniform, and this was, this was understood basically in the 70s and 80s. At that time, the anisotropies in the CMB had not yet been detected, and experiments were looking for the anisotropies, and each experiment found stronger and stronger limits. Just found a very uniform CMB. And each one reported just stronger limits at 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. It was expected that to get to here, that we should have had fluctuations of like maybe 1% in the CMB. Of course, that's not the case. So this is, I think, sort of the first really compelling evidence, certainly on a cosmological scale, for the existence of some sort of matter which has gravity, which forms gravitational potential wells, which should have been present here, but is not emitting radiation. It's not a part of the plasma. It's not interacting with the baryons very much except through gravity, and is not coupled to the electromagnetic interaction. So we can look in the elementary particle database to see what candidates we might have for dark matter, and we do have some dark matter among the known fundamental particles. That's the neutrinos. So they do fulfill this, in certain respects, they fulfill this role They do not have strong interactions or electromagnetic interactions, of course. They do have mass, so that's all good. The trouble is the masses are too small to form these gravitational potential wells. Because the neutrinos are so light and they're so highly relativistic, they tend to smear out the gravitational potential wells. They escape from the gravitational potential wells and tend to blur them out rather than reinforce them. 30 years ago, it was not known what the masses of the neutrinos might be, and at that time, perhaps it was plausible that maybe one of these guys was heavy. It might have been a good dark matter candidate. But today we know that's not the case. So we need something that's kind of like a neutrino, but heavier. And very crudely, we can just kind of imagine a heavier particle that's like a neutrino. Maybe it has weak interactions, and let's call it a weakly interacting massive particle or a WIMP. And so that's kind of what we're looking for. That does not have electromagnetic interactions, but is heavier, would have been not so relativistic, and therefore would have been seeding these gravitational potential wells in the early universe. So if it's the case that we have this new particle that we've not yet seen in the laboratory, but it's kind of like a neutrino, let's say, and it's heavier, we can ask the question, does that particle fit into the standard model somehow, or does it extend the standard model somehow? We can ask the question, does it have sort of particle physics interactions that we would recognize in a laboratory if we saw it? And if it does have particle physics interactions, then it should be the case that if you run the clock backwards to the very early universe, when the universe was just a nanosecond old, the universe was very, very hot, its temperature maybe was 100 GeV at that time. If that dark matter does have particle physics interactions, then at this temperature we would expect it to be annihilating and creating along with the ordinary matter. So it would have expected it to be a part of the plasma at that time. So let's imagine that there's some mystery particle physics interaction between these dark matter particles and the normal matter that we know and love. So at this age, the dark matter should have been annihilating through this mystery diagram. So we'd have had dark matter annihilation in a normal matter, and then of course normal matter colliding in the plasma would be creating dark matter. So this diagram would have been going back and forth in both directions. And in equilibrium, thermal equilibrium, we would expect it to be going at the same rate, basically. So the dark matter would have been in thermal equilibrium, and it would have had a large abundance at this time. So if we then run the clock forward, starting at something like 1 nanosecond, the universe was 1 nanosecond old, up to 10 or 100 or 1,000 nanoseconds, up to a microsecond, then because the universe is expanding and space is expanding, these dark matter particles will be becoming more dilute. They'll be finding each other less often. The universe is cooling as well, so the normal matter collisions that are creating them will turn off. And because this creation process will turn off first, the abundance of the dark matter particles will start to drop, the number abundance. That's what's being plotted on the y-axis here as a function of time. Then eventually the annihilation also turns off, and that's because of the diluteness of the WIMPs. They simply won't find each other very much anymore. And so there will be a relic abundance that's left over from this process. And this, of course, is the famous freeze-out scenario for the production of dark matter. The nice thing about this scenario is that the amount of dark matter we have is going to tell us about this annihilation cross-section. Because if the annihilation cross-section is small, then the annihilation will turn off kind of earlier, and you'll be left over with a lot of dark matter, so to speak. And if it's a large annihilation cross-section, then what's left over is just going to be a very, very kind of thin residue. And so, of course, we've measured how much dark matter there is in the universe, so we know what we're looking for. We're looking for an abundance that's right here. And this argument is telling us that if this hypothesis is true, that this dark matter has particle physics interactions and was a thermal component of the plasma in the early universe, then it's telling us that there should be an annihilation cross-section that's right here. And of course, the famous observation here is that the annihilation cross-section you need is kind of typical for the weak nuclear force, which is that's a nice outcome for this story, and it speaks favorably in favor of this hypothesis. In other words, it's not necessary to imagine a completely new fifth force, for example, in this scenario. You can imagine that it's just that these dark matter particles exist and that they interact with ordinary matter through the normal weak nuclear force that we already know of. So in that sense, this scenario is kind of efficient or minimal or something like that, right? So of course, the difficulty today, as I'll talk about in a moment, is that we've now set such constraints on what these cross-sections could be that there starts to be some tension with this picture. Okay, and I'll talk about that in a moment. But this is the picture we'd be left over with In the universe today, when you look up in the sky and you look at, for example, a spiral galaxy, you see all the stars that are emitting light, you see the dust and the gas, but we're picturing, we have lots of evidence that that galaxy is in fact immersed in this, this dark matter halo, which in this artist's conception is shown as this sort of blurry blob here. We can write down a few characteristics of these dark matter particles, whatever they are. They're gravitationally bound to this galaxy, just like just like the stars are. So for our own Milky Way galaxy, in the neighborhood of the Earth, we know that our sun and the Earth orbits the center of our Milky Way galaxy at a few hundred kilometers per second. What that means is that dark matter particles that are also gravitationally bound to the center of our galaxy should also be orbiting at the same speed. And that means they're moving at just a fraction of the speed of light, so they're highly non-relativistic. We know what the spatial density of this dark matter should be, because we know how much dark matter the Milky Way has. The number is that you should have about 300 GeV of dark matter mass per liter of space. And if you hypothesize that the particle has, say, 100 GeV mass, that means you've got 3 of these things in every liter of space. And of course, what we mean there is because we picture this being a uniform distribution. We picture these wind particles being right here in the room with us or in the laboratory with us, even for an underground laboratory. So we expect that the dark matter particles are there in this picture. The de Broglie wavelength you can infer by assuming what the mass is. So if you take a 100 GeV hypothesis for the mass, since you know the velocity and the mass under that hypothesis anyway, you can then calculate the de Broglie wavelength. And it's going to turn out to be larger than a Fermi, which is important for the direct detection experiments, because that means that they're going to coherently scatter off of all of the nucleons if they're going to interact with atomic nuclei through the weak nuclear force. So the scattered cross-section should go like the atomic number squared of the target material that we use. So this is the particle physics that we're looking for. The dark matter annihilates in this direction in this picture. We can look for that annihilation in the modern universe, of course, and that's what experiments like the Fermi telescope do, or other high-energy gamma ray experiments like the Hawk experiment. So when Fermi looks at the gamma ray sky, it's looking for dark matter to be annihilating, for example, in the center of our galaxy, or in the center of neighboring satellite galaxies, or maybe in the Andromeda galaxy, a nearby galaxy like the Andromeda galaxy. So it's looking for this annihilation process, and typically the picture here is that the dark matter should be annihilating into something like maybe like B quarks or C quarks or maybe tau leptons or something like that. But that those particles then decay and give you some pi zeros, for example, and those pi zeros, of course, give you gamma rays. So when they look up at the gamma ray sky, they're looking for this annihilation process that is proceeding somehow, probably largely through pi zeros, is what they're sensitive to. So when you look at the Fermi catalog, there's, as I mentioned, there's kind of at least two ways to go about this dark matter search. You can look in the center of our galaxy for an overabundance of these gamma rays coming from the center of our galaxy, which is there is in fact evidence for some excess of gamma rays at the center of our galaxy. But the systematics are very difficult there, and it's an open question. People are still pursuing whether or not we can attribute that excess to dark matter annihilation. The more straightforward analysis is to look at satellite galaxies of the Milky Way, where there's not a lot of ordinary matter emitting this kind of background stuff. So if you look at dwarf spheroidal galaxies that are orbiting the Milky Way, they don't have much ordinary matter, but they have a high abundance of dark matter. So the Fermi collaboration does that. They look through their catalog for excess gamma rays from places in the sky that are known to be have Milky Way satellites. They don't see any excess in that analysis, so they set a limit on what the annihilation cross-section might be. The magic annihilation cross-section that we look for to explain the abundance of the dark matter is this value here. It's a few 10 minus 26 in these units. The solid line shows the limit that they placed. This is from 2015, this is a few years ago. This is past 8 data. And so if we take this limit at face value, then it sets constraints on the existence of WIMPs below about 100 GeV. Of course, nobody would take this limit entirely at face value because, of course, astrophysics is complicated. But nevertheless, this is a really important data set. I think the thing that really speaks favorably for this effort, this campaign, is that in this case you do have a very strong expectation for what cross-section it is that you're looking for, which is obviously really powerful. In direct detection experiments, of course, we're trying to approach this particle physics by seeing the dark matter scatter off of our detectors. So now we have time to go in this direction. in this diagram. So we want the dark matter particle, which we believe is in the laboratory anyway, passing through the laboratory. We want to see it scatter coherently off of our target material in that direction. In principle, it's going to scatter, if it has ordinary weak interactions, it should scatter both from atomic electrons and from the nuclei in our detector. But because of this coherent scattering effect, we expect that the overwhelmingly more likely process or more frequent process is scattering from the atomic nuclei. So we'll look for these nuclei to be sort of spontaneously recoiling. That'll be our signature. That's the signature that we're looking for. Sort of unexplained anomalous excess of atomic nuclei recoils in the data. The backgrounds will be mostly from radioactive backgrounds like gamma and beta particles, and those interact primarily with the atomic electrons. So we'll consider atomic electron events to be a background that we try to reject. So now we looking at this particle physics diagram, of course, we're looking for the cross section in this direction. That's the process we're looking for. We do know what we would look for in this direction. That's what the Fermi telescope does. It'd be nice if knowing the annihilation cross section in that direction would then point us to one particular direct detection scattering cross section that we should search for. It would be nice if that were the case. Then you could imagine building a targeted experiment who's designed to probe that special cross section and either observe it or rule out this whole WIMP scenario. But the fact of the matter is that without knowing the details of what is in this question mark, what's in this particle physics diagram here, we can't say what the direct detection cross section should be. It can come out over many orders of magnitude depending upon what the details are of the new physics that's in there. And that means we have to search for many orders of magnitude of parameter space. So this was, of course, this has been understood for a very long time. This is these are some comments that were made in a paper 18 years ago, the year 2000. The name of the paper, title of the paper is Reevaluation of the Elastic Scattering of Supersymmetric Dark Matter. This is a plot from that paper. The solid lines up here are showing the limits on the direct detection cross-section that have been placed by experiments like UK dark matter collaboration, the Heidelberg experiment, CDMS, early CDMS data had placed constraints on the existence of WIMPs up here. The green blob there is the Dama effect. Of course, CDMS and other experiments were beginning to probe the Dama effect at that time. What these authors pointed out is as follows. Our results fall considerably below many of the possible predictions in the literature. In other words, they're exploring the supersymmetric parameter space, and they're saying that for these models that they're considering, which are the constrained, minimally symmetric supersymmetric standard model, that the parameter space that's most favored is far below where the experiments were probing at that time. They say this may discourage some faint-hearted experimentalists. They go on to say we should not want our experimental colleagues to be too downcast by the long road they appear to have to cover in order to probe the minimal universal MSSM framework utilized here. However, we think it's best to have in mind a plausible and realistic target sensitivity. So there's lots of, this is lots of opportunity for clever experimentalists to explore interesting parameter space, and it was far below what the experiments at that time were probing. So here's a plot that shows the the advancement in the experimental state-of-the-art for a 50 GeV WIMP as a function of publication date. So that paper that I just mentioned was in the year 2000, so it was about right here. And the experiments at that time, like CDMS, were probing something between 10 to the minus 42 and 10 to the minus 41 in cross-section at that time. So these solid points here are experiments that have reported results since then. And of course, this is a log scale, obviously. So the experiments have been improving rapidly. So we've now covered maybe a factor of 100,000 in cross-section space in the last 18 years. These solid red points are recent results from the Lux experiment, the Xenon 1-ton experiment, and X experiment. The Xenon 1-ton experiment they're going to report new results very soon. They did not report them at UCLA last month, but they promised them within about a month. So we do expect that within, by the end of the month of March, we'll have new results from Xenon 1-ton. They'll either see something or set new limits that would be down here. The LZ experiment is projected to come in a few times 10 to the minus 48. So we are largely probing, a large fraction of this supersymmetric parameter space that has long been suggested as the most promising kind of supersymmetric model space. So of course we don't see anything, and we do get some press. We put out press releases, and we try to get people like the New York Times to write articles. When we had the first result from Lux in 2013, the New York Times wrote a headline for us: "Dark matter experiment has detected nothing." Researchers say proudly. So you can, in these headlines,
It's
you can
better
kind of
than it
detect,
used to be.
yeah, you can kind of detect a note of discord. I mean, the journalists here are not quite sure why we appear so happy and so proud to have not discovered dark matter. Here's another headline from 2016. This one's from the UK. This one says, "Lost in space, supersensitive 7 million pound Lux dark matter detector finds nothing. Ambitious and very costly experiment fails to solve one of the great mysteries of the universe."
Does Rupert Murdoch know?
I don't know, that's a good question. It's possible. Yeah, it says a News UK company, right? So that would be is that like News Corp?
That was kind of only partially a joke.
Maybe he does know this, it's possible.
No, because hopefully the White House doesn't Twitter about the.
Oh, this is fake news, Bob, don't worry. They also say here, despite perceptions that their experiment had failed, researchers hailed it as a success because it allowed them to rule out several theories about the makeup of dark matter. So sometimes we have trouble communicating why we appear to be satisfied with our experiments, although we're not finding dark matter. You know, obviously, as everybody in this room knows, we feel successful if we carry out an experiment and it probes the parameter space that we intended to probe. And that was the case for the Lux experiment, and it's been the case for many experiments, CDMS included. And so, you know, so we do feel like we're making progress because we are probing the parameter space that we wish to probe. Whether or not WIMPs actually exist in that parameter space is it's kind of above our pay grade. So we don't get too downcast, I hope, by whether or not nature has chosen to put a WIMP there.
Just a quick footnote: he has verified that Rupert Murdoch does in fact know.
There you go. So now, who owns the New York Times? Let's see, the Solzbergers, I guess.
That's true. Yeah.
They're the publishers or something. Yeah. Okay. So this is what we're looking for. We're looking for anomalous nuclear recoils. This is an energy spectra that we would expect from WIMP scattering on different target materials. Energy on the x-axis here, and then event rate on the y-axis, logarithmic event rate. So all these materials have kind of smoothly falling spectra. So it's kind of exponentially falling. So we typically think of it as an exponential spectrum. There's no particular turn on, so it does start right at 0 and goes down, which means that there's a premium paid on getting your threshold of your detector very, very, very low. So the lower your threshold, you get sort of, in some sense, you kind of get an exponential payoff for lowering your detector threshold. You can use different target materials, and lots of different target materials are used in different direct detection experiments. We're using xenon, and we like it because, for a number of reasons, but because it's the highest atomic number of these 5 possibilities, that means that the scattering cross-section, or the scattering rate, has an advantage for xenon compared to these other target materials. Now, as the folks in CDMS will tell us, of course, there's advantages to germanium and argon as well. But in this particular respect, xenon has an advantage, and that's one of the reasons why we like it. There is this sharp feature in the spectrum out at between 80 and 100 keV, at least for the xenon 132 isotope. This is just the form factor of this nuclei. We would not expect to see this. You can see that the rate for this feature is down by many orders of magnitude from the rate that we would actually measure. You know, if we saw events from WIMP scattering, we would first see them here. So we don't expect to actually see this strong feature. It should be there in principle if WIMPs exist. And it just reflects the size of the nucleus. These other targets would also have similar features further out in energy. So we need an experiment with a very low threshold. This shows an example of the kind of threshold that we achieved in Lux. So this is the beta decay spectrum of carbon-14. So we put a carbon-14 source into Lux. Carbon-14, of course, is this famous radio dating isotope. It has a half-life of 5,500 years. And it's a beta decay. Its endpoint is 156 keV, which is fairly low energy even from a nuclear physics perspective. So the endpoint of this beta decay spectrum is out here at 156. There's a bump out here because when we took this data, we had a second calibration source in the detector at the same time that was making a line. It's a gamma line at 164. But it's this smooth beta decay spectrum here, which is the carbon-14. I show this just to point out that The spectrum you're seeing from there all the way to the end is the true carbon-14 spectrum. In other words, our threshold, the threshold in lux is only 1.3 keV. So we have a very sharp turn on at very low energy, and I mean obviously the experiment has been designed to do that, so that we have this best sensitivity as we can to WIMPs, which are going to show up, which we expect to show up close to the low energy threshold of the detector in a first observation. We would expect it to be there. So this is the animation that shows how the liquid xenon TPC works. So we have a bath of liquid xenon, a cylinder of liquid xenon, which is this purple stuff here, the liquefied xenon. It's in a cylindrical cryostat. Above the liquefied xenon, there's gaseous xenon. That's up here. We put photomultiplier tubes on the bottom of the cryostat, immersed in the liquid, and also in the gas phase up here. So if a WIMP elastically scatters off of one of the xenon nuclei, then we get a flash of scintillation light, primary scintillation light, which we observe mostly on the bottom photomultiplier tube array. We also get some free ionization that's created, and we have a vertical electric field to drift that free ionization vertically. We extract it out into the gas phase, and once it gets into the gas phase, it makes proportional scintillation, and there's a second flash of light at that point, which localizes the charge, localizes the entire event in X and Y. So from the drift time that we measure between the first scintillation and the second scintillation, the S1 and the S2, and from the localization of the charge from that secondary proportional scintillation, we get all three X, Y, and Z coordinates for the event. And then also the charge and the light are also providing energy information. So we're measuring energy and all three coordinates. So on an event display, an event like this in Lux looks something like this. The so-called S1 light, so time is on this horizontal axis here. This is in microseconds. This S1 light is typically a handful of photoelectrons. In this particular event, maybe there was half a dozen photoelectrons. The depth in this plot, in this event display plot, is PMT number. So this is showing you like one photoelectron in a handful, maybe 5 or 6 different PMTs. So we see that small, very tenuous kind of photoelectron signal as the S1 signal. Then the charge is drifting, so we see nothing during that drift time. But when the charge gets extracted, in this particular event, it got extracted 20 microseconds later. Then we get this proportional scintillation, which is much, much, much larger because in that case, every atomic electron or every ionization electron that we get into the gas, we can now, it will now make many, many photons. So there's a natural kind of gain process that happens. So one electron can give, for example, 25 photoelectrons in Lux. And so we get a large S2 signal, which localizes the event X and Y and measures the magnitude of that charge signal. One of the challenges of the detector is that because we're trying to see events on the very lowest energy we can, we've got this gain turned up pretty high. So we get pretty big, fairly large S2 signals, many thousands of photoelectrons, or tens of thousands of photoelectrons even. But we still need all the electronics in the whole DAQ chain to be sensitive for just single photoelectrons at the same time. So that's one of the experimental challenges. So that's what an event looks like. We can reject, of course, the backgrounds are from gamma particles and beta particles, and in the Lux experiment, the dominant background was from gammas. If you simulate how gammas propagate through liquid xenon using a J-NUT simulation, you'll see something like this. In this particular simulation, there's a cubic meter of liquefied xenon. This is a cubic meter of liquefied xenon. We have, in this drawing here, we've got 200 photons, 200 gamma particles of this energy, 2.6 MeV. So, a factor of 1,000 higher than the energies where we're going to look for dark matter. You can see how far the photons are able to penetrate. These gamma particles are able to travel, what their mean free path is. In general, they can travel tens of centimeters, so they're highly penetrating when they're MeV energies. At 500 keV, the absorption cross-section is rising, in particular from Compton scattering and from photoelectric effect. It's rising. So the gammas are no longer quite so penetrating. At 100 keV, it's risen dramatically, and at this energy, these gammas only travel maybe a centimeter or so. At 1 keV or 2 keV, where we're actually going to look for the dark matter, the gammas are only going to be traveling microns. So what this means is that the liquid xenon is very insensitive to the very lowest energy X-rays or gamma particles. In other words, if these gammas attempt to come into the detector from the outside, they'll be absorbed in the very first layer at the very exterior of the target volume. And so we can reject them simply by requiring that the events not be near the edge of the detector. So we call that self-shielding. And that's sort of the simplest form of self-shielding. It's just that the gamma cross-sections are behaving in a virtuous manner. So this is kind of good for doing dark matter searches. It's difficult to do searches for rare events that are at 2.6 MeV because of this large gamma penetration length, but that's not the case in the X-ray region where we're kind of looking for dark matter interactions. A second effect that we also call self-shielding has to do with the kinematics of these events. So if a gamma particle is attempting to come into the detector from the outside, for example, if it's created in a photomultiplier tube or if it's created in the cryostat from trace radioactivity in those components, then the gamma it'll penetrate, but it can only penetrate if its energy is high enough. If it's an MeV gamma, it can penetrate. In this plot, this is a side view of our liquid xenon bath in the Lux experiment. So the width here is about 50 centimeters, and the depth is about 50 or 60 centimeters. So if this gamma particle comes in, it can penetrate if it's got enough energy. So an MeV gamma is able to penetrate to the center of Lux. But it's only a background for dark matter if it deposits only a keV of energy. If it deposits a full MeV, that's kind of fine. That'll make it hard to do double beta decay searches, but for searching for dark matter, we're not searching for events of that energy. So we only care about it from a dark matter perspective if it deposits just a fraction of its energy, maybe 0.1% of its energy. So because that's what we're looking for, this means that in the scattering event, the only gammas that are problematic are the ones that forward scatter. So such a small energy deposition means a very small scattering angle. And this is very good. This is good news. This is virtuous because this means that this gamma now has to travel the full length of the detector. And if it interacts a second time before leaving the liquid xenon bath, we'll reject the event because we'll see the multiple site event. So we're not going to keep events in the dark matter search that have multiple interactions because dark matter does not interact multiple times. So this means that because of this kinematic argument, the only gammas that are problematic are those that deposit a tiny fraction of their energy and then are able to, just through luck, basically, through quantum mechanics, I suppose, rolling the dice, are able to cross the full volume of the detector and escape unseen while scattering only once. So this is a really powerful rejection scheme. It's difficult for gammas to satisfy these conditions. This is a simulation that shows where the remaining events show up when you apply these cuts, this energy cut and this single scatter cut. The color is a logarithmic plot. So this is log base 10. So the blue is 10 to the minus 4 in rate compared to the red. So there's lots of gammas interactions like this at the edge of the detector, but there's not much in the middle. And this is, in my opinion, this is the primary thing that makes the liquid xenon technology work. And the other important thing is that this argument just gets stronger and stronger as the liquid xenon bath gets larger and larger. So by going from 10 kilograms of liquid xenon to 100 to 1,000 to 10,000, this exponential suppression of these backgrounds just gets stronger and stronger, gets exponentially stronger and stronger and stronger. And this is why it's not that the experiments we're building now are much lower in background rate than the experiments from 10 or 15 years ago. It's not that we have exponentially suppressed the materials. The materials are cleaner, but they're not exponentially cleaner than they used to be. It's what makes the background rates lower is that this kinematic rejection is very powerful, and just simply having the detector be larger naturally does this suppression for us. We can also do particle ID in Lux, so we can separate electron recoil events from nuclear recoil events. We do it by measuring the charge in the light signal, which in general are going to be different for nuclear recoil events versus electron recoil events. In particular, nuclear recoils will make heat, which we're not sensitive to. We don't measure that in Lux. And they'll deposit about half of their energy into heat. We don't see that. So that means that when we measure the charge and light signal, or if we take the ratio of the charge we see to the light that we see, if you plot it as a function of the light that you see, you get these bands, these sort of famous electron recoil band, which shows up in this part of the scatter plot. For nuclear recoil events, there's also a band. The nuclear recoil band is below the electron recoil band, and that's kind of shown here. This solid red line is showing you where the center of the nuclear recoil band is. So it's displaced from where the electron recoil band is. These dashed lines are showing you the 10 to 90% excursions from the center of the electron recoil band. So in liquid xenon, we get an electron recoil rejection factor of something between 200 to 500. Actually, it gets up to about 1,000 in certain portions of the energy parameter space. So this is sort of the last thing that we can do to reject these gamma and beta events that remain in the data set at the end of the day. So, so this is some pictures of the Lux assembly, which I showed at the beginning as well. So the photomultiplier tubes were loaded into copper PMT arrays here. You can see the size of the experiment here. Lux is now a museum piece. If you go to South Dakota and you go to the visitor center in Leeds, South Dakota, you go to the Stanford Lab Visitor Center, you can see Lux on display there. I don't know if I put that picture in here or not. It's got they took the Lux cryostat, they cut a big hole in it so you can see inside, and they put some structures inside so you can see what the interior of the detector looks like. Of course, we're underground in South Dakota. We're at the 4850 level underground in the Stanford Underground Research Facility. So we're in the Davis Cavern where Ray Davis did the famous home state solar neutrino experiment. This is a picture of what Lux looked like when it was installed. When it went in September 2012. So this is so it's hanging basically inside this water tank. When the picture was taken, there was no water. But when we run the experiment, we fill this with pure water, and the pure water acts as a passive shield for neutrons and gamma rays that will attempt to come into the experiment from the laboratory or from the cavern walls. So this is the Lux WIMP search data from the second run of Lux, the second data set from 2014 to 2016. What's plotted here is a scatter plot of charge on the y-axis and light on the x-axis. This is a log scale over here. And the blue lines are showing you where electron recoil events should show up, and the red line is showing you where nuclear recoil events should show up. You can see there are a handful of events in the nuclear recoil area, but this is known to be spillover from the electron recoil band, plus events from the walls of the detector that are understood and known to be there. So we analyze this data with a likelihood fit, and the likelihood fit tells us that this data is perfectly consistent with no WIMP interactions at all. So this sets a limit on the level of anomalous nuclear recoils from WIMP scattering, or a limit on the cross section for WIMP scattering. And that's where it came out. This is from our paper from 18 months ago. The solid line is showing the Lux limit at that time. This has been improved since that time. I think I have, yeah. So for example, the Xenon 1-ton experiment, which is our colleagues that are doing a similar experiment in the Gran Sasso laboratory. They reported first results in May of last year, and they have exceeded the Lux sensitivity. There's also the Panda X experiment, which has also exceeded the Lux sensitivity. So these three curves are showing those experiments, including the Lux experiment. So they're all kind of in the neighborhood of each other. But these experiments, the Xenon 1-ton experiment, the Panda X experiment, are continuing to take data, and we're going to hear new results from Xenon 1-ton very soon. As I mentioned when I started, they have 10 times as much data on disk as what they've reported here, and they do promise that they'll tell us their results later this month. So it'll be exciting to hear what they've seen or what they haven't seen in that much larger data set. So I'll say a few words about the technique we use to look for the dark matter and to understand the detector technology. So one of the key features of doing the experiment is this electron recoil of rejection. To know what an electron recoil event looks like in the experiment or what a nuclear recoil event looks like in the experiment, it's necessary to characterize these two bands. We can do that by putting radioactive sources into the experiment, so we can observe for a known source what an electron recoil event looks like or what a nuclear recoil event looks like. A typical way that we might do that is to put a gamma source like cesium-137 next to the cryostat. So in fact, there's tubes, source tubes, that are hard to see here because they're actually transparent, but they are here on the outside of the cryostat that allow us to lower gamma sources next to the TDC. And for example, we do this with cesium-137, for example. So we can do this and we can calibrate the electron recoil response of the detector using these gammas. But this is not a very effective calibration method. The reason being that the whole point of this experiment was that it's not sensitive to gamma rays that are coming in from the outside. So once we apply our single scatter cut and our low energy event cut and our fiducial cut, there simply aren't many events left anymore. That's the whole point of the design, right? Gammas coming in from the outside don't cause many events. They will cause many events at the edge of the detector, but of course we want to know what the background events will look like in the bulk of the detector, not just at the edge. So we needed, so for the LUX experiment, I mean, LUX was kind of the first liquid xenon experiment that was really large enough that it was kind of somewhat intolerable to try to attempt to calibrate it with these external gamma ray sources. So for LUX, what we did was we injected into the bulk of the fluid, into the bulk of the liquid xenon, a beta decay calibration source, which was more advantageous. We used tritium, which is a radioactive form of hydrogen. Its Q value is 18.6 keV. So it's a beta decay source that cuts off at 18.6 keV. We searched for dark matter between about 1 and 8 keV. So this is this tritium beta decay spectrum. It's kind of in the heart of the dark matter energy range that we're looking for. So virtually every event in this tritium data set is useful for characterizing the electron recoil response of the detector. It's also nice that tritium is a single beta source. It doesn't have any complicated X-rays and other things like that, so it looks genuinely like a single scatter event. It does have the troubling issue that it has a long half-life. Its half-life is 12 years, so when you inject it, you can't just wait for it to decay away. You're not going to wait many factors of 12 years.
Just put in old tritium.
So we, what's that?
Just put in old tritium.
Old tritium. Just put in the ones that are going to decay.
Right.
That are going to decay fast. Yeah. If you can identify them beforehand, there's a Nobel Prize in it for you if you can. Our friends in quantum information would be interested in that. What we did was we purify it back out with a purifier that's constantly operating to purify the xenon anyway. There's a whole purification system that is always operating 24/7. In the case of the tritium, we put it into a molecular form of methane. So methane is CH4. So you replace one of the hydrogens with tritium. Of course, tritium is hydrogen, so chemically this is fine. So we put in this tritium-labeled methane, and the methane then comes back out in the purifier. And the nice thing about methane is that it doesn't want to hang around inside the detector. It doesn't want to stick to surfaces, and so it's happy to come out when we purify it. So the first time we did an injection of tritium into LUX was in August of 2013. We were a little bit shy about it. I mean, we'd done many, many benchtop tests and many studies to convince ourselves that it was going to come back out. But the very first time we injected into LUX, of course, we proceeded with caution. So we injected a little bit. This is the event rate of the detector as a function of time. We injected a little bit, and then it came back out due to the purification system. We then waited about a week and made sure that everything was okay. Then we injected some more of the higher activity, and again, it purified back out. The purification time constant is like 6 hours at max. And then, of course, the background rate went back down to the nominal value, so we were happy about that. That's what we expected to happen. What this data tells us is how much light and how much charge you get from beta decays in liquid xenon at the particular LUX electric field, which is 170 volts per centimeter. So this is what beta events look like in liquid xenon. There's lots of fluctuations event by event between charge and light. This big blur that you're seeing, it's not the detector energy resolution, it's that there are genuinely large fluctuations from one event to the next and how much charge you get and how much light you get. And this data set allows us to characterize all of that. The energy spectrum of the tritium is exactly as expected, and since we know exactly what the energy spectrum should be, we can compare our data to the expected energy spectrum, and that allows us to do all sorts of things like observe the low energy threshold of the detector. We can see that in this data. We know that it turns on at 1.25 keV because of this tritium decay source, and we can study the corrections to the data. So it's a very powerful data set.
So there is more deep.
Yeah, I was going to ask about that. At 6?
Yeah, you know what? Don't know. I guess it's about 3.5 sigma. This is the residuals plot. So that's 3.5 sigma is that particular thing. And yeah, you could say there's something going on here. So there's something correlated going on there, and I don't know what it is.
Yeah, because it's got 3 bits up, just below 5.2.
Yeah, that's right. So what we do here to make this energy plot is we measure the charge, and we measure the light, that makes the scatter plot. Then you project it along these diagonal lines to make the energy spectrum. Because A nice feature, a curious and interesting and nice feature of liquid xenon is that it's the number of photons plus the number of electrons that measure the energy, not either one. Either one by themselves is not a particularly good measure of the energy, but the sum of the number of photons and the number of electrons is a good measure of the energy. And so these diagonal lines are showing the energy projection, basically. So we take this data and we project it into this spectrum. And there's some care and some care has to be taken to do this. In particular, you have to understand what the precise projection direction should be, for example.
Yeah, it looks like something funny is happening between 5 and 7 in the light blue region. So go to the right a little, yeah, so up in that cloudish thing.
Mm-hmm. It's possible, yeah, it's possible. So this characterized for us the location of our electron recoil band in Lux. The other band that we need to characterize is the nuclear recoil band. We do that with a neutron generator. To get neutrons into Lux, we have a neutron generator which we can place outside the water tank. So this is a picture of the neutron generator. It's a fusion generator. It's fusing together deuterium. Deuterium plus deuterium fusing together gives a neutron, a monoenergetic neutron of 2.45 MeV. And that's powerful. Knowing the input neutron energy is 2.5 MeV is very powerful. To get that neutron to go into the detector, we have to create a hole in the water, because the water's purpose is to absorb neutrons. So they won't get there by themselves. But we made a hole in the water. We have a tube. In the case of Lux, we had a tube. It's in the past. The tube was usually sat on the floor of the water tank. The tube is filled with nitrogen, and it's sealed at both ends. When we want a neutron calibrate, we lift up the tube. It's on guy wires, and we lift it up. And we make a hole in the water that runs from the tank, the outer wall of the tank, over to the cryostat. Then what happens is that an army of graduate students spends the next few weeks making small adjustments to the angle and orientation and position of the neutron generator, and in principle also to the water hole, so to speak, to get the neutrons aimed right down through the tube, which of course you can't see from the outside, right? So there's a lot of, there's 6 degrees of freedom on where the neutron generator should be, its position and its angles. And so they try something, they've surveyed it, so they have a strong expectation for where it should be. But getting it correct in detail is a little bit of trial and error, basically turning it on, looking at the event rate and the trigger, right, the trigger event rate, and then making an adjustment and doing this this can take a while. But it works. And you can measure the charge and light yields of liquid xenon to nuclear recoil events as well this way. So this shows the charge yield for nuclear recoils down to, I think the very lowest energy bin here is, that is 1 keV. So this is like, it's between 0.6 and 0.7, I guess, keV is the very lowest measured charge yield for electrons from nuclear recoils. The light yield is measured down to 1.1 keV. So that tells us the efficiency of the detector for nuclear recoils. It tells us the range of WIMPs that we're sensitive to, and it tells us the size of the WIMP signal that we should expect. So that's the story with Lux. To make the experiment more sensitive, it's not worthwhile to run it longer because we need to. It's not worthwhile to improve the experiment by a factor of 2 by taking 4 times as much data, for example. We're trying to cover logarithmic parameter space. So a factor of 2 for 4 times the length is not a useful trade-off. So you have to make the experiment larger so you have more target material. So that's why we're building the LZ experiment, which has 10 tons of xenon. Here's the size of the thing. The size of LZ compared to the size of Lux. Lux was about 400 kilograms. So this is about 25 times more liquid xenon. The fiducial mass of LZ will be 5.6 tons. And we're going to place it into the same water tank where Lux was located. So this shows the drawing of what LZ will look like. So there's the 10-ton liquid xenon TPC in the center. We surround the Lux TPC with a neutron veto, a liquid scintillator, a room temperature organic liquid scintillator, neutron and gamma veto, which is shown in green here. This is liquid scintillator has been loaded with gadolinium. Gadolinium is this metal that has this famously large neutron capture cross-section. When it captures neutrons, it creates about 8 MeV of gamma rays. The liquid scintillator will then create scintillation light from the interaction of the gamma rays. and we'll observe that scintillation light with a new set of photomultiplier tubes that's observing the liquid scintillator veto. So this is an entirely new feature of LZ, and it was really demanded by the fact that LZ would have had some 10 or 12 neutron nuclear recoil events in its final data set if we did not have this veto. So it would have been, the Lux experiment did not have a veto and did not have neutron backgrounds. The LZ experiment does, basically because the LZ has a much larger target mass, so it presents a much larger target for neutrons. We also run LZ longer. We're going to run it for 3 years rather than 1 year. So simply by observing longer, you get more neutron events. And then also we have more photomultiplier tubes in LZ. So it's going to be more neutrons created by the photomultiplier tubes and more neutrons created by the surfaces as well. So with the outer detector vetoing these neutron events, our neutron backgrounds are down below 1 event, as I'll show you in the backgrounds table in a moment. So we formed the collaboration in 2012. We got CD3 approval last year, about 1 year ago, in January 2017. We'll be ready for data taking according to our schedule in the spring of 2020. So we're 2 years away from taking data with LZ. And because we're 2 years away, that means that lots of final equipment is being fabricated now. The PMT array is made out of titanium in LZ, and that shows the actual titanium PMT array. This shows some of the PMTs undergoing testing, cold testing. All the PMTs are in hand. They've all been tested, so they're all, in fact, what we're doing right now is we're gearing up to load all the PMTs into the titanium arrays. The cryostat is fabricated. This is the 10-ton cryostat. It's fabricated in Italy. It's shipping to the US later this month, actually. And it'll be on site in South Dakota in April. We're starting to make we're making grids for the experiment, field rings, and we have a prototype TPC that's shown over here. So this shows the effect of the outer detector from a simulation. This is, again, this scatter plot is showing a side view of the right-hand cylinder that makes up the liquid xenon cryostat. And the points are showing where nuclear recoil events would be if you did not apply the veto that's supplied by the outer detector. So without the outer detector, we would still have about 3.2 tons of fiducial liquefied xenon kind of in the heart of the experiment. But by applying the veto of the outer detector and also the skin, liquid xenon skin, we recover, this is where the events end up in that case after we apply the veto. So we go from 3.2 tons of liquefied xenon to 5.6 tons. So this is a worthwhile investment to make. The efficiency of this outer detector for neutron rejection is 97% from simulation. That's what the simulation says. So, and actually, here's one of the water tank, or one of the acrylic tanks that will hold this liquefied gadolinium liquid simulators under fabrication of Reynolds in Colorado. So Reynolds is the company, for example, that made the acrylic sphere for the SNOW solar neutrino experiment. Here's our background budget in kind of in the form of a table. All the detector backgrounds are shown in this upper portion here. The physics backgrounds, like double beta decay, 2 neutrino double beta decay, and astrophysical neutrinos are shown down here. One of the interesting things about LZ is that we will have 250 events from PP solar neutrinos in the WIMSearch data set. And that's in fact the second most common thing we have. The second most common type of event we have is PP solar neutrino events. The most common event we have is radon, which is somewhat less interesting than PP solar neutrinos. But that'll be our most common electron recoil background anyway. We're also going to have some coherent scattering of boron-8 solar neutrinos on our nuclei, which I'll remark upon in a moment. The bottom line is that we'll have about 1,200 electron recoil events and about 1 nuclear recoil event in the final data set from our backgrounds. And then we can apply, of course, we can apply electron recoil discrimination to reduce the electron recoil background.
Are you taking natural abundances as 136?
Yes.
That's like
8%.
8%.
Yeah. And the half-life is 10 to 21 years.
You could actually purify that more. Yes. Yes. Or no?
Not to get rid of the xenon 136. You'd have to isotopically separate it if you wanted to get rid of the xenon 136.
Okay.
So
Is that something that you're just not
it's
working with?
expensive.
It's
Because
expensive.
that's what a double beta case
Yeah.
would do. They would isotopically separate it and take the 136. But it increases the cost of the xenon by some factor of 5 or 10.
Okay.
For us, the xenon is $15 million, and it's the largest single cost of the experiment. So, yeah. This is a simulated data set of what a 40 G, where a 40 GeV WIMP would show up in, the charge versus light parameter space. So there's the background events, mostly due to radon and krypton and PP solar neutrinos and the electron reflow band. Boron-8 solar neutrinos will cause coherent scattering. We'll see those events right on our threshold down here, just a handful of photoelectrons. But we do expect to have a substantial number of them, some 3 or 4 dozen of them in our 1,000-day data set. So we're interested in these events, and there's interesting neutrino physics that can be done with these events because it is coherent scattering, which is it's a standard model process, but it was only observed the first time last year by a coherent experiment, of course, right here at Texas A&M. Of course, the minor experiment is also going after that physics as well. So there's a lot of interest in this kind of neutrino physics right now. So this is our spin-independent WIMP sensitivity from the paper that we posted on the archive a few weeks ago, which is here, the archive number. So the solid line is showing our 90%, our median 9% limit that we could set on WIMPs if there's no WIMP interaction in the experiment. This gray blob is showing some of that constrained, minimally supersymmetric standard model parameter space that I talked about at the beginning of the talk. So we're probing a lot of this. We're getting pretty close to what's called the neutrino floor, the neutrino discovery limit, where the experiment, so WIMP experiments that are sensitive down here, of course, will see lots and lots of nuclear recoils from atmospheric neutrinos, and supernova neutrinos are what contribute mostly to this background or this region of parameter space. And the boron-8 solar neutrinos are what's contributing down here which act as a background for light insertions. So we'll be turning on the experiment, first data in the spring of 2020, and we're going to run until 2025. So this is the parameter space we'll explore. It's about a factor of 50 below what Lux and Xenon one time and Panda X have so far explored. So I think I just want to stop there. There's a picture of our collaboration from our collaboration meeting on site in South Dakota last year. And I want to thank you for the invitation, and be happy to take any more questions that you have.
Any more questions for our speaker?
What kind of field you're about to collect the electrons in the ULC? 2 meters. So you're collecting over 2 meters or so.
Yeah, so it's a 1.5 meters, and the field is 300 volts per centimeter is our baseline field. So it's a cathode voltage of 50 kilovolts, and
You have breakdown, things like that, arguments.
of course we're very concerned about it. So one of the things that we do with our prototype TPC is do high voltage tests in liquid xenon. We also have a separate high voltage test set up at LBL, which uses liquid argon. So this is one of the huge efforts of LZ compared to Lux, I would say, has been in characterizing the electric field performance of the entire TPC assembly. In LZ, the cathode connection comes in from the side. It penetrates through the cryostat from the side. In previous experiments, the cathode cable would have been like a snake coming down here along the side of the TPC, but bringing it in from the side means that the electric fields are much smaller in that region between the cryostat and the TPC. This, in fact, was one of the contributions that James White made to LZ. One of many contributions he made was he pointed out that this would be a better geometry for getting the cathode high voltage in. James also pointed out that we should put our heat exchanger outside the detector. That's what's shown over here. That's where the liquid xenon is condensed. In Lux, that condensing happened inside the detector, but James argued successfully that this should be outside the detector. James also worked out the scheme of assembling the TPC on the surface at SURF in a special clean room on the surface at SURF. That's where the TPC assembly will be done. Then the whole detector is going to be tipped on its side to load it into the shaft and to bring it down. So it'll come downstairs to the underground on its side, and then we'll be righted again in the Davis cavern. And that was another, that was James's vision for how to make the largest possible TPC we could, and also to be able to do assembly on the surface where logistics are obviously a lot easier. So James played a lot of, sort of the basic architecture of the experiment was largely James's vision from about 2012 and 2013, right before he passed away.
You just put the time capsule in, and I was thinking about putting James's picture inside the time capsule.
Harry put James's picture in the time capsule. So James's pictures are in time
There's boots as well.
There's just
Somebody
a
sent me a
little
picture of something that was
His
on the
boots are
control.
on the shelf in the
Control room, right?
downstairs dressing area.
There's no
I have
question
his
about
brass
collection,
tag.
electron collection.
Say again?
Electron collection, or is it trapping? There is no issue of lifetime of
Electron lifetime.
Yeah.
Yeah, the requirement is that the electron lifetime should match the Lux electron lifetime. It does not need to substantially exceed the Lux electron lifetime. So we aim for only 800 microseconds actually. Lux got up to a couple of milliseconds, so Lux actually be better than that. So the requirement is that that the attenuation length be no more than 1 drift distance, which is not that. We do not think that should be a limiting factor. We expect that will be achieved.
Oh, sorry, go ahead.
When you're collecting the data, and you showed the possible detections, do you also attempt to filter those with different frequencies, like sidereal frequencies, solar frequencies, lunar frequencies, anything, to see if there's any periodicity in the noise?
Yeah, once we have 1,000 days of data, certainly we'll look for annual modulation, daily modulation. In the Lux experiment, we only reported an annual modulation search result a couple weeks ago, actually. Yeah, but certainly we will do that. I'm certain that somebody will do that with the LT data as well. Of course, the annual modulation search is interesting for many reasons, including the fact that the DAMA experiment sees an annual modulation, and so most other experiments who have several years of worth of data want to do an annual modulation search.
There's another question. Can you go back to your table of 136? Yeah. So do you just like live with radon and krypton? Is there any way to?
Yeah, that's a good question. So we live with it after spending millions of dollars to suppress it.
Okay.
So
and that's worth millions of dollars, but Xenon 136 is not probably, is that because it's just?
Yeah, that's right.
Okay.
So this 67 events is, this is out of a budget of 1,200 events, electron recoil events.
Okay. And these are all like hundreds of keV, right?
Let me bring up so it goes down to 0 here, but I can show you the energy spectrum from
Yeah.
our sensitivity paper. So this is the simulated energy spectrum. So this does not include the detector energy resolution. This is just the J-on energy spectrum, but it shows all the different components. The Xenon 136 double beta K is this red or orange line, and it's going down like this. We're doing the dark matter search down here at the, this is 0 to 100 kV. We're only searching between 1 and 8 kV. So it's only this very, very lowest portion of the Xenon 136 that's important.
Yeah.
Krypton 85 is there, and radon 222 is here, and there's a zoom-in plot that shows the actual.
I guess like what if I had some hypothetical idea of trying to understand like solar neutrino physics with that green line right there? Is it just like radons and game over for that, or I mean, is there anything?
So we're very interested in, and I'd love to talk to you about it, about what we might be able to do with the data that's not a WIMP search. In particular, it'd be great. There's going to be thousands of PV solar neutrinos. I mean, we've read your paper, so we know how many events there's going to be.
I mean, see, just specifically with like electron recoil signal, like very high energies, like this is a different sort of flavor or something.
Yeah. So the challenge will be the radon, because the events will be essentially indistinguishable from beta decays from the radon decay chain. The challenge will be to understand the radon backgrounds in the detector and understand the Krypton 85 backgrounds in the detector. Event by event, those events will be indistinguishable from PP solar neutrinos, but you measure the sum of them. Measuring the sum will not be a problem. So you measure the sum of them, and then the entire challenge will be convincing yourself from other measurements that you're doing that you understand the radon contribution to it, and you understand the Krypton contribution to it, and then you would say the PPs are what's left over.
Okay, so are those lines including your $1 million of backgrounds?
Yeah, so this is Krypton 85 after we've suppressed it.
Okay, that's after $1 million. Okay.
Yeah.
And the radon too, or no?
Yeah, so for radon, yes, so the radon as well, that's radon 220. The one here is more important is the solid blue, radon 222. Yeah, so we suppress the radon by screening all the detector materials for radon emanation. So we have 4 screening sites in the collaboration, 3 of which in the US and 1 of which is in the UK. And every item that touches the xenon gets screened for its radon emanation. And this is what we think we can get to.
Okay.
So that's what we think is practical to get to in terms of the radon level. I'm personally very interested in this. I've
Yeah, we'll
talked
talk
to you about it.
about it.
Because we're going to have, this is the first dark matter experiment where we can, do this astrophysics.
Yeah, I mean, this is like below the current works, like detection sort of thresholds for solar
Exactly,
energy.
yeah.
So this is like there's something to think about.
Absolutely, yeah. Yep.
Let me see if I understand correctly. So in the S1, S2 curves, in the older approaches, there was a signal region and you count the signal region, if I understand.
Yeah.
But in the newer approach, you have an event by event weighting of likelihood of signal versus mechanism.
That's right. I would say that what you said is exactly right, and I would say that that's been made possible because of these calibration methods that we developed that fully characterize both the location of the band, of the 2 bands, and their width, and the fluctuations. So we really feel like we have a good understanding of all of that, such that we can do a statistical analysis of the entire parameter space and be able to be quantitative about where the signal event should show up.
That's pretty nifty to not just have that boundary effect between the hard transition.
Yeah, that's right. So earlier experiments would have done a more, often did a more sort of counting experiment kind of analysis, which is fine, but we feel like, we've convinced ourselves and others that we can take full advantage of all the information and not just do a kind of a hard cut and count.
Any other questions? If not, let's thank Carter.